Ever feel like you're trying to take a sip from a fire hose when you're learning something new?
Yeah, definitely.
Today, we're all about making complex information refreshingly clear as we deep dive into a research paper from 1985 about something called Boltzmann machines.
Okay.
Now, before you think 1985,
Right.
is this dial-up speed learning? Hold on. This
Like, yeah.
paper,
Uh-huh.
with Geoffrey Hinton as one of the authors, is considered foundational to modern AI. We're talking about the roots of how we teach computers to learn.
Mm-hmm.
Not with brains, but with networks.
What's fascinating is that this paper reads like a blueprint for the AI advancements we see around us today. Hinton, often called the godfather of AI, won the prestigious Turing Award for his work in this area. We're about to step into his workshop, so to speak, at a pivotal moment.
Okay, so let's unpack this. What exactly a Boltzmann machine?
Imagine a network of light switches, each one a tiny piece of information. These switches are connected, and the strength of the connection tells you how much one switch agrees or disagrees with another. Now picture these switches flipping on and off randomly, influenced by their neighbors and those connection strengths. That's a Boltzmann machine in action.
So the switches are like neurons in a brain,
Uh-huh.
and the connections are like the synapses.
Exactly. What's remarkable is that through this seemingly chaotic flipping, the Boltzmann machine is actually seeking its lowest energy state. It's trying to find the most stable and efficient arrangement of those switches to represent the information it's given. And that, believe it or not, is the key to solving complex problems.
So it's not just random noise. There's a method to this madness. But how does this search for stability actually translate to learning and problem solving in AI?
That's where the researchers got really clever. They designed a task called the encoder problem to study how these machines learn. Imagine you have two people trying to communicate, but they can only send messages through a low bandwidth channel, like using smoke signals. The encoder problem is about finding the most efficient way to compress and send information through that limited channel.
So how did they use Boltzmann machines to tackle this?
They created a Boltzmann machine with 3 groups of units, similar to those neurons or switches we discussed. 2 groups represented the sender and receiver, and a third smaller group acted as that limited communication channel.
So one group for each person, and a smaller group in the middle representing the limited bandwidth of the smoke signals.
Precisely. The fascinating part is that the Boltzmann machine, through its process of finding its lowest energy state, that stable configuration of switches, actually learned how to efficiently encode and transmit information, even with limited bandwidth.
It's like it invented its own secret code to deal with the limitations. But how does this secret code actually work? Give us a peek behind the curtain.
It's all about finding efficient representations of data. Imagine you want to send a complex message, but you can only use a few smoke signals at a time. You need to find a way to compress that message, to represent it using a limited set of symbols. That's what the Boltzmann machine learned to do. It figured out how to take the information from the sender, represent it in a compressed form that could be sent through the limited channel, and then decoded by the receiver.
So this wasn't about just storing information like in a database. It was about understanding and manipulating it in a way that maximized efficiency.
Exactly. And what's even more remarkable is that it learned this code entirely on its own. The researchers didn't pre-program it with the solution. They simply set up the problem, the sender, the receiver, the limited channel, and let the Boltzmann machine loose.
So by searching for that lowest energy state, that optimal configuration of its switches, it stumbled upon a solution that even the researchers might not have anticipated.
Exactly. And that's a key insight here. Boltzmann machines aren't just about brute force computation. They're about enabling a system to learn from experience, to discover its own solutions, much like humans do.
That's incredible. They were onto something big back in 1985, weren't they? It's like they discovered the ancient blueprints for a futuristic machine that's now everywhere.
Absolutely. This paper laid the groundwork for a whole new way of thinking about artificial intelligence, and its influence is undeniable in the technology we use today.
Well, on that note, let's shift gears from the history lesson to the here and now. This isn't just an academic exercise. This research has real-world implications, right?
Absolutely. Remember we were talking about the encoder problem being like finding the most efficient way to communicate through a limited channel? That's essentially what much of our modern technology relies on, transmitting information efficiently.
Right.
The internet, your smartphone, all rely on these principles of finding efficient data representations, a concept rooted in the work on Boltzmann machines.
It's like discovering the ancient blueprints for a futuristic machine that's now everywhere. You don't necessarily see the blueprints themselves, but their influence is undeniable.
That's a great analogy. It highlights how crucial fundamental research is. Sometimes those theoretical breakthroughs take decades to translate into the technologies we use daily, but the impact is often profound.
Okay, so we've established that Boltzmann machines are a big deal, and that this 1985 paper was way ahead of its time. But let's get even more concrete. What were some of the specific findings from their research?
One of the key things they discovered was the impact of network size on a Boltzmann machine's ability to learn and solve the encoder problem. They experimented with different numbers of units in that hidden layer, that communication channel we discussed.
So like trying different sizes of bottlenecks
Mhm.
to see how much information the machine could still squeeze through.
That's a great way to put it. They discovered that even with a relatively small hidden layer, meaning the communication channel was very restricted, the Boltzmann machine could still find clever solutions. It might take longer to learn, but it could adapt and find ways to represent the information effectively.
That's fascinating. It's like the machine is saying, give me a challenge. I'll find a way to make it work. So it's not just about the size of the network, but also about how it's used, how it adapts to the problem at hand.
You've got it. It's not just about brute force computation, it's about finding elegant and efficient solutions. This paper highlighted those capabilities and demonstrated how, even with limited resources, Boltzmann machines could achieve impressive results.
I'm starting to get a sense of just how groundbreaking this research was. It wasn't just about building a bigger, faster computer. It was about fundamentally changing how we think about intelligence and learning.
Exactly. This paper challenged the prevailing view at the time, which focused on more rule-based approaches to AI. Instead, it showed the power of letting a system learn from experience, from data, and discover its own solutions.
It's like the difference between memorizing a phone book and actually understanding how language works. But how did they prove this? What did their experiments look like?
One of their key experiments involved, as we've discussed, the encoder problem. To test the Boltzmann machine's learning and adaptation, they presented it with a series of communication challenges, much like giving it different messages to encode and send through the limited channel.
So they'd activate a specific unit in the sender group, like lighting a specific smoke signal. And the machine had to figure out how to represent that signal, using only the limited resources of the communication channel.
Exactly. And on the other side, the receiver group had to learn how to decode those signals and correctly identify which unit in the sender group had been activated. Think of it as a complex game of charades, but with artificial neurons instead of awkward hand gestures.
And what did they find? Was the Boltzmann machine able to crack the code, so to speak?
What they found was remarkable. Even with very limited communication bandwidth, the Boltzmann machine successfully learned how to encode and decode information with a high degree of accuracy. This was a major finding. It demonstrated that these machines could learn to represent and manipulate information efficiently, even in complex and challenging environments.
So they weren't just theorizing. They were getting their hands dirty with actual data and experiments. It sounds like the Boltzmann machine excelled at this encoder problem. Were there any other significant findings from their research that we should highlight?
They also explored something called noisy clamping during the learning process.
Noisy clamping. That sounds a bit intense. What is that?
It's actually about introducing a bit of controlled chaos into the learning process. Remember how we talked about the Boltzmann machine trying to find the lowest energy state?
Yeah.
That optimal configuration of its internal connections?
Yeah, like finding that perfect position on a beanbag chair.
Exactly. But what if that beanbag chair had a few surprises hidden inside? By intentionally introducing some noise into the data during training, the researchers found that the Boltzmann machine could learn more robust and generalizable representations.
That's so interesting. You'd think giving the machine messy data would make it worse at learning, not better.
It seems counterintuitive, but think about it. We don't just memorize facts. We learn from experience, which is often messy and unpredictable.
So noisy clamping is like giving the Boltzmann machine a broader perspective, helping it see the forest for the trees, so to speak, and preventing it from getting stuck on the specific details of the training data.
You've got it. It's about encouraging the machine to extract the underlying patterns and principles that hold true more generally. It's like teaching the machine to think critically, not just regurgitate information.
Self-organization, the encoder problem, noisy clamping, all these groundbreaking concepts packed into this 1985 paper. It's clear that Hinton and his colleagues were really on to something special here. What else did they test to prove the Boltzmann machines were the real deal?
They also looked at how well these machines could generalize their knowledge to new, unseen data, a classic test of true intelligence. It's one thing to memorize facts, but another thing entirely to apply those facts in novel situations.
So how do they test this?
They trained the Boltzmann machine on a subset of data and then measured its performance on a separate, held-out data set that it had never seen before. It's like showing it half a deck of cards and seeing if it could figure out the rules of the game and then play successfully with the other half.
What did they find?
The Boltzmann machine generalized its knowledge to new data reasonably well, showing it wasn't simply memorizing the training data, but rather learning underlying patterns and principles. Even back in 1985, it was showing signs of actual learning, not just mindless mimicry. And that's a crucial distinction. Memorization has its place, but true intelligence lies in adapting, generalizing, and applying knowledge flexibly in new and unexpected situations.
This all sounds very promising, but were there any limitations to this early research? What challenges were they still grappling with back then?
One major challenge was the computational power available at the time. Boltzmann machines, especially as they grow in size and complexity, require significant computational power to train and operate effectively. And computers in 1985 were much slower and less powerful than they are today, which limited the size and complexity of the Boltzmann machines they could realistically experiment with. They had these groundbreaking ideas, but the available tools weren't quite up to the task of fully exploring their potential.
So their research was somewhat constrained by the technological limitations of the time. But even with those limitations, they could demonstrate the promise of Boltzmann machines and lay the groundwork for future advancements. Aside from computational hurdles, what other challenges did they face?
Another challenge was the learning process itself. Training a Boltzmann machine, especially on complex tasks, can be time-consuming and computationally intensive, even with today's supercomputers. It's not just about having the raw ingredients. It's about the art and science of combining them to unlock their full potential. Finding the optimal network structure for a given task was also challenging. Remember how they experimented with different numbers of units in the hidden layer? Well, finding the ideal network architecture for a specific problem wasn't always straightforward.
So it wasn't just a one-size-fits-all solution. Different problems, different data might require different network designs.
Exactly, and this is still an active area of research in machine learning, designing and optimizing network architectures to achieve the best performance on specific tasks. It's like choosing the right tool for the job. You wouldn't use a hammer to tighten a screw or a screwdriver to chop down a tree.
Okay, so even though this research was groundbreaking, there were still challenges and limitations. But it seemed like those challenges, rather than discouraging them, inspired them to push the boundaries even further. So to wrap up this part of our deep dive, let's zoom out a bit from the technical specifics and consider the bigger picture. What are some of the most significant ways that Boltzmann machines and their descendants have changed the world as we know it?
It's amazing to think that something as complex as artificial intelligence can be traced back to these elegant networks of light switches.
It really is. And you know what's remarkable? This 1985 paper we've been dissecting, it's not just a dry technical document. There's a certain elegance, a kind of poetry to the way they describe these Boltzmann machines.
I see what you mean. It's like they stumbled upon a fundamental principle of nature. This idea of a system naturally seeking its lowest energy state, like a ball rolling down a hill until it finds a resting point.
Exactly. And that this simple principle, this drive towards stability and efficiency, could be the key to understanding not just how machines learn, but maybe even how our own brains work. That's a mind-blowing thought. It's like we're looking for the same underlying principles, the same elegant solutions in both the natural world and the artificial world.
Precisely. And that's what makes this whole field of research so exciting. We're not just building machines, we're trying to unravel the mysteries of intelligence itself.
Well said. And on that note, we'll wrap up this deep dive into Boltzmann machines. We hope you've enjoyed exploring this fascinating topic with us, and we encourage you to keep those intellectual sparks flying. Until next time, happy learning.